invitation, and I want to thank very much the organizers for giving me the opportunity to talk today about some characterization of biomaterials. And this work was done in a very strong collaboration with Wing-Shin Tay, César Leroy, and Andrew Ranking in Paris, in France. So the materials we will talk about today are called pathological calcifications, or kidney stones, in other words. And it represents a major problem worldwide, especially in the Western countries. And just to take an example, in France, the related costs associated to these pathologies are estimated over 800 million euros. These are complex objects to characterize because they are intrinsically, structurally, and chemically complex, as they contain minerals, but also organics, such as fatty acids, triglycerides, and proteins, and they correspond to what we call the hybrid organic-inorganic materials, exhibiting complex interfaces between the organic and the inorganic components. In terms of minerals, we will focus today on two main families. The first one is related to the calcium oxalate, which are of prime importance in the constitution of kidney stones at various levels of hydration, namely the mono, the di, and the trihydrates. And also we will focus a little bit on calcium phosphates, and among them probably the most famous one, which is hydroxyapatite, which you can find also in your bones and teeth. So several years ago, we decided to establish a strong collaboration with physicians at the Tenon Hospital in Paris. And these people are nephrologists, and they are at the head of a huge collection of kidney stones, more than 50,000 samples coming from all over the world and exhibiting all possible compositions. And the goal of these people is to establish new methods of characterization in order to improve the diagnosis, in order also to invent new methods to prevent these diseases. And curiously, NMR and a fortiori dynamic nuclear polarization are clearly underused by this community. And that's why I decided to go a little bit in this field. And that's the outline I propose to you. First of all, I will show you that NMR can be considered as a unique platform of characterization. Then we will show that it's possible by simply rotating the sample at the magic angle in the rotor. It's possible to follow in situ transformations. And then I will go back to, I will follow with a more technical point related to sensitivity enhancement, as we are dealing sometimes with low mass samples. And finally, I will show you some snapshots of what we can do with dynamic nuclear polarization in this particular field of research. So here you have the classical and the standard carbon-13 NMR spectra related to a kidney stone. And you can see that it's a complex spectrum, but you can completely edit it by playing with the contact time. And you can, for certain contact time, overestimate the protein part. And you can also, by playing again with the contact time, you can overestimate the inorganic part corresponding here to the calcium oxalate in its monohydrate phase. There are as well a very mobile species, and you can edit them very efficiently by using JMAS-derived experiments such as INEPT. And in this case, it can be proved that they correspond to fatty acids. And if you want to further characterize this fatty acid, you go to simple double quantum filter Cozy experiment, and you can assign very safely all the correlation. If you want to look at the interfaces between the organic and inorganic components, then you can switch to traditional dipolar recoupled experiment, proton-proton, double quantum experiments, such as back-to-back, which is very robust. And in this case, and in favorable cases, you can extract correlations corresponding to the interfaces. So what is very important also for physicians, it's the speed. Is the experiment fast to obtain? So they were really interested for sure by proton solid state NMR experiments. And I show you here that if you use, for instance, Dumbo homonuclear decoupling, but you can use other decoupling schemes, it's really easy to distinguish the fingerprints corresponding to the monohydrate in red, to the dihydrate in blue, and the trihydrate in green. And in this case, it's even possible to assign the chemical shifts and to interpret the chemical shifts by taking into account, first of all, the structures of the materials, and we decided to optimize them at the DFT level in order to have the best description of the proton networks. Why the proton networks? Because this is the key for the assignments. These H-bond networks are completely different from one hydrate to the other in terms of number of contacts for a given proton, and also in terms of distances between oxygen and protons, meaning that you can, in a certain way, decide if one particular H-bond network is rigid or not. And if it's not rigid, you can allow flipping of a water molecule, so you introduce dynamics, and then it's possible to completely interpret the chemical shifts, the isotopic chemical shifts obtained for the three phases. So now I switch to the second part, dealing with in situ transformation. If you spin rather slowly at the magic angle, let's say 5 kilohertz, then for the three hydrated phases, here you have the fingerprints, which are clearly distinguishable first, and the number of sharp peaks is directly related to the number of inequivalent sites in the asymmetric unit. But as soon as you spin faster, let's say 30 kilohertz, using a 2.5 millimeter probe, then you see that starting from the dihydrate, which is characterized by the blue spectrum, after a certain time of evolution, you will have a complete transformation of a sample into what I call for the moment an intermediate phase with two peaks, which are a little bit broader than the initial ones. And then if you allow the sample to cool, in fact, by decreasing progressively the spinning speed, you end up with the 4 peaks, which are completely characteristic of a monohydrate phase. So in other words, you have monitored in situ without temperature regulation, for sure. You have monitored the transformation of the dihydrate into the monohydrate. This is completely irreversible, but what is completely irreversible is you start from this structure, you spin faster, you end up again with this intermediate phase, and if you go back down, you will retain the structure of the monohydrate. So what about this intermediate phase? It was, in fact, if you look very carefully at the literature, it was mentioned 2 times. And the assignment was the following, the attribution was the following: it should correspond to an amorphous calcium oxalate phase. And I was a little bit skeptical about this because we have clearly the distinction between peaks, and we don't have any broad peak corresponding to an amorphous sample. So, in fact, if you go back to the spectrum corresponding to the monohydrate phase at low spinning speed, let's say 5 kilohertz, in fact, you have always to consider the combination of the first phase with sharp peaks superimposed to a second phase characterized by 2 broader peaks. And you see that probably these 2 broader peaks correspond to the intermediate phase we have discovered in the last slide. And in fact, in order to assign definitely the peaks, we decided to go to spectral editing by using the standard inversion of polarization experiment. Why? Because we know from the XRD data that the oxalates are connected to proton corresponding to the water molecule, but some molecules are closer to the proton than the other ones. So by editing, it will be possible to extract the chemical shift corresponding to the carbon-13, which are more coupled to protons. And in fact, that's what we did here by increasing the inversion time, which is here. And you see that the whole deshielded part of the spectrum corresponding to the purple rectangle is inverting much, much faster than the other one in the green rectangle, meaning that the three purple peaks are closer to protons than the three green ones. And in fact, we could make it a little bit more quantitative by simulating all the spectra by increasing the inversion time. And you see, the conclusion is exactly the same. You have always this inversion of the most shielded part of the spectrum included, and that's very important, included the broad component, which is represented here and which is here negative for this particular inversion time. So, all in all, we have now a full interpretation of the carbon NMR spectra for the monohydrate. First of all, there is a structure characterized by 4 peaks, which are really sharp. Look at the range of the chemical shifts. It's all the story lies within 2 ppm. And in fact, it corresponds to the standard structure, which is already reported in the literature for decades, with this space group, P2(1)C, with 4 inequivalent sites. And we can divide these 4 inequivalent sites in 2 families. 2 of them are close to the protons, and the 2 others are remote from the proton. That's what we have proved very efficiently by inversion of polarization, but we have to co-add a structure. And this structure, in my mind, before a paper I will comment briefly, was quite unknown. And in fact, in 2020, a group of theoreticians in Israel proposed a disordered COM phase, which is based only on DFT calculation, no proof, no experiment, and so on. But the idea is that they introduce a statistical space group, which is completely different from this one. And in this case, there are only two inequivalent sites for carbon-13. And as we have disordered, it could be the origin of the broadening of the peaks. In fact, if you look very carefully at a large number of calcium oxalate monohydrates obtained by synthetically, either by using rapid precipitation or slow diffusion through a gel, then you see that you have always to consider the superposition of 2 phases, one characterized by 4 sharp peaks and the other one by 2 broader peaks. And what was very interesting from my colleague at Tenon Hospital is that if you look carefully at these fingerprints, which correspond obviously to synthetic samples, they look very, very like the same as in the case of natural samples, namely kidney stones, meaning that we are able to characterize the kidney stones from the carbon-13 NMR spectra into families. And what we are doing now is to make it a little bit more systematic in order to establish a new diagnosis tool, meaning if I have a given carbon-13 NMR spectrum, am I capable of explaining this shape, for instance, by former diseases for the patients. Now I will switch to sensitivity enhancement. As I told you, we are facing sometimes the problem of samples, which are very important, but for which the mass is intrinsically low. So I introduce here a second part of the kidney stones, which is called the Randall's plaque. What is this Randall plaque? The Randall plaque is sort of aggregation of hydroxyapatite. It's very small, and nobody knows exactly the structure of this. But what we know is that the plaque is developing here at the bottom of the papilla in the kidney, and it acts as a nucleus for the growth of a bigger calcium oxalate kidney stone. If you look carefully at this picture, you have here in the middle, in white, the Randall plaque. The dimensions are all sub-millimeter, meaning that the corresponding mass is, let's say, in between 100 and 200 micrograms, okay? So in order to analyze this kind of samples with very low mass, we decided to use a concept invented by Dimitris Sakellariou called magic angle coil spinning. The idea being to put the sample in a capillary here in the center and to wrap around a microcoil, okay, which is here, and you see the characteristic size of the microcoil and soldered to a chip capacitor. And the ensemble capillary chip and a microcoil is put in a standard 4 millimeter or 3.2 millimeter rotor, spinning at the magic angle in order to retrieve the resolution. And what Dimitris proves very nicely is that in this case, you increase the signal-to-noise ratio, mainly because the filling factor of your system is close to 1 in this case. How is it possible to characterize your microcoil from the RF point of view? You can simply record a notation, which is here for phosphorus and for a given power. And from the T90-degree pulse, you can extract the efficiency of the coil, and you can even calculate an estimation of the gain in time, which is always at least 10 in the case of proton and phosphorus for a few euros. So the entire equipment here is a few euros. And I will show you in the next slides that it works for masses as low as 100 microgram. Just an example, so to prove that it works, in 4 hours we were able to record a complete DHMQC experiment, which is highly robust to correlate, for instance, proton and phosphorus. Here the detection was on the proton side. We used a particular recoupling scheme, but you can use another ones in order to improve the sensitivity of your experiment. And by playing with the recoupling time, we were even able to show up some correlation which were, I would say, unexpected, and we are still trying to understand them. Now, the last part of my talk will be devoted to some snapshots related to DNP, and I will give you at least 3 reasons to do DNP in the framework of biomaterials. The first one is related to low natural abundance and low gamma nuclei. You could tell me, okay, you are working with biomaterial, what about calcium-43 NMR? Calcium-43 NMR is a nightmare from the sensitivity point of view due to 2 things. First of all, it's a low gamma nuclei, and the natural abundance is really small. It's 0.14%. But by using the DNP and by selecting the correct DNP juice, it's possible, you all know that it's possible to enhance considerably the signal-to-noise ratio. And in this case, we were able to record in 4 hours the first 2-dimensional experiment. It's an headcore type correlating a calcium dimension to a proton dimension with a distinction here between sites, and it was then possible to assign the correlation peaks by going back to the structure of hydroxyapatite. The second reason is that, again, due to the huge gain in signal-to-noise ratio, by using DNP, you can very fastly record double quantum, single quantum experiments. Here, I focus on a very complex problem, which is the substitution of biological appetites by carbonates. There are 2 sites which are possible, the A site corresponding to the OH groups and the B sites corresponding to the phosphates. And it's very difficult to know how the carbonates are into the structure, are located into the structure. And without going into the details, if you look very carefully at this double quantum, single quantum carbon-carbon experiment, it was possible to exclude definitely the association of A sites, and the most favorable association was a clustering of B sites, and we were even able to detect A-B association by looking at this kind of experiment. And the third and last reason is you can go back to low mass experiment, as I told you. Here we are looking at one unique Randall plate, you see, with the DNP juice, and we tried the experiment. And in fact, in 7 hours, we had this headcore experiment correlating the phosphorus dimension to the proton, and the signal-to-noise ratio is quite good. And from the structural point of view, it's important to us because it was the first time that we demonstrated that, yes, indeed, it is an apatite. The Randall plate is an apatite, but to our surprise, the cores of the apatitic structure are highly disordered, much more disordered than cores observed in teeth, and bones. Just to finish my talk, it's possible also to go to first principle calculations of what I call here realistic structure. What do I mean by realistic structure? Not only looking at the bulk of the hydrated calcium oxalate, but also at the interface. So playing with water molecules or organics, and also a bulk of a large number of water molecules and organics, let's say above the surface. Here, so it was published rather recently in collaboration with Fred Tillins. Here are some keywords of the methods we used, and we demonstrated in this case a particular role of water, and also the fact that the first layers of solvation here had to be treated at DFT level. And then it's possible to go back to DNP experiments. You can do assignments by combining this structure prediction with GPO, and we had yesterday a beautiful talk by Jonathan Yates. And here, just two-dimensional experiment, 1 hour experimental time, and the possibility to completely assign the proton and the carbon-13 in the monohydrate. And from a chemical point of view, and I'm interested in currently, you can choose the DNP juice, in fact, in order to check the heterogeneity of the samples. They are heterogeneous, and by playing with the DNP juice, you can enhance the role of one component, for instance, here the protein part, and you can completely underestimate the role of the oxalate. So if you want to completely understand and to explain this spectra, then you have to go again to a description to the interfaces. So you have to model them and to calculate the GPO calculations. So that's the end of my talk. These are the conclusions. I hope I have shown you that yes, proton and carbon and nuclei, are good targets for physicians, especially nephrologists, and we have a very nice collaboration now. It's possible to follow in situ the phase transformation of all the calcium oxalate hydrates, and we have shown that this is subtle. I would say this is subtle, and we even demonstrated the presence of a new polymorph, which had been proposed based on DFT calculation. I have showed also that MAX and DNP clearly open new tracks for research. With this, I will thank my students who worked a lot on this project, all my collaborators, and again, all of you and the organizing committee for the kind attention. Thank you very much. I have more time. Just, yes. Yeah, for questions.
Yeah. Sorry, I will apologize to Christian because the timer was a little bit off. So you have extra time for those questions. So questions for Christian Bonhomme.
In the last part of your talk about DNP, so what size crystals or particles are you measuring? Do you find that there's a problem if you're measuring micro crystals?
That's a good question.
Because of the surface?
There is all the work on hydroxyapatite was with nanoparticles. So I synthesized them, 15 nanometer roughly in one dimension, looking like rice grain. You see, elongated. And in the second case with kidney stones, you take the sample and retry. And in fact, you have big crystals, you have small organic parts and so on. So that's complicated.
Thanks.
Hi, wonderful talk. I was wondering if you comment on the size of the coil when you're doing these microcoils for your formula in terms of length and how much sample volume you're getting in there.
Yeah, that's so it depends on the nucleus you want to match.
Sure.
So the number of turns of the wire and the pitch depends on the frequency of the Larmor frequency, but you can calculate it. So 1 millimeter roughly.
Okay.
And the diameter of is internal diameter is roughly 500 or micrometer or less. We went down to 350, but you can imagine that it's highly fragile. It's handmade, okay, under a microscope. And in terms of volume, I would say it's much less than a 0.7 millimeter rotor for sure. And in terms of mass, if you take the density of hydroxyapatite, for instance, you end up with roughly 150 microgram, roughly.
Sure. Yeah, I was kind of curious if you could compare the sensitivity of going to smaller diameter rotor and coil, but having it be elongated, just to get similar sample volume.
Yeah, that's a good point. The tests we've made show that probably this design is better than, let's say, 1.3. I have no data with 0.7. I decided to do them before COVID, and COVID came, so no experiment.
Sure.
But for 1.3, definitely this is better.
Okay, great. Thank you.
Thank you.
Actually, can I follow up? So you showed that there was a capacitor at the end of that. So how do you balance that in the rotor?
You have to be very, very precise about the quantity of soldering you put and so on. But I have to confess that my student, Winshin Te, she has gold in the hand. I don't know if I can translate it like this, but she's preparing 10 microcoils, and the 10 microcoils spin. I would say spin at 5 kilohertz, no problem. Above, sometimes we break the microcoils. The diameter of the wire is 35 micrometers, so it's less than a hair.
Good craftsmanship. Other questions for Christian? Yeah, Eric.
Christian, very nice work. Concerning the solid state transformation, you mentioned calcium oxalate as a MOF. Can you comment on, one, on the porosity, and two, is the transformation you observe, is it purely temperature driven, or is it also pressure driven?
Yeah, that's a super question. Yeah. What I have in mind soon is to do experiments with variable rotor diameters in order to play with the centrifugal force. I would say that pressure should have an impact, Here, without temperature regulation, you have this evolution, okay? If you regulate very actively the temperature, then pressure plays a role because you have still transformation, even at low temperature, okay? Your second question is very interesting. Indeed, this is the only natural MOF, the dihydrate. I discovered this 2 weeks ago, let's say, by reading the literature. What is interesting is you transform a zeolitic structure into something which has no porosity. So you completely destroy the structure, the zeolitic structure. And that's why you have as an intermediate these two peaks phase. You see what I mean? Because if you go back, if you start from the trihydrate, you make exactly the same experiment, but you start with a trihydrate, which is not a zeolite. Then you go continuously, you lose water, and you go continuously to the monohydrate without the appearance of the intermediate phase. So the intermediate phase is something, let's say, disordered, and that's the results of the explosion of the zeolitic structure. I mean, that's what I think. I am not in the rotor.
With that, and in the interest of time, let's thank Christian one more time for. All right, I am delighted to introduce Tamar Wolf, who's coming to us from the Weizmann Institute.
Hi. Today I'd like to talk about progressive saturation of proton reservoir, or PROSPER, for indirect cell-light transition detection. And our goal was naturally sensitivity enhancement. And we were inspired by a method commonly used in liquids, which is called chemical exchange saturation transfer, or CEST. And in CEST, we use an abundant species to enhance the NMR signal of dilute species. And you can see in this nice animation, so the way CEST works, you saturate the dilute species, and then by means of chemical exchange, you actually you indirectly saturate the protons of the abundant species, and then you enhance your dilute species. So this is the type of spectra you usually achieve in CEST. They're called Z spectra. And it's essentially a mirror image of your regular spectrum. and your dilute species are enhanced in proportion to the exchange rate. So we were wondering if these type of CESS-like experiments, if they would be possible in solids. And in solids, we don't typically have free water, but we did notice a few points of similarity to CESS experiments. One of them is that the dilute Labelle protons that are usually found in CESS, then you can be analogous to dilute X spins that we have, or alternatively, the pool of protons that are coupled to these X nuclei. And then instead of the abundant pool as water, we would have an abundant distant decoupled protons that are marked here in blue. And then also, usually instead of exchange, the analog would be spin diffusion between these two pools of protons. So the type of experiment that we envisioned was instead of selective RF saturation, a type of frequency selective CP-based saturation of the protons. And then we have our target X nucleus NMR spectrum. And we envisioned progressively sweeping and then achieving this indirect detection on the protons. So here we made an assumption that the saturation or depletion of the protons would be proportional to the signal of the X nucleus at this point, and that's something that we still need to prove. And I'd also like to state at this point that the published work that I'll be talking about in the first part of this talk was led by Michael Dorosevic, which is currently finishing his PhD in our group. So the first type of sequence that we thought might be able to work was repeated Hartmann-Hahn CP with a flipback pulse and then a readout. But this type of, version of the sequence had a few problems, namely that it required high RF on the protons to get good spin locking. Otherwise, we suffered from decrease in the intensity because of generation of higher order coherences. And then in turn, the high RF on the protons, we encountered a few problems with that. So we had to match it with high RF on the X channel, which is typically not possible for low gamma. Then it would also require very high duty cycles. And finally, our goal was to perform indirect detection. So this would result in very poor resolution. So we were looking for an alternative. And then we came by a pretty old idea of adiabatic demagnetization in the rotating frame, or ADRF, which is used to generate dipolar order. So essentially, in the sequence, we convert Zeeman order adiabatically to dipolar order. And in Zeeman order, the order of the spins is determined by the external magnetic field, whereas in dipolar order, the ordering of the spins is determined by the local dipolar fields of the protons. And the nice thing for us about dipolar order is that once you generate it, it lives for a time scale of T1D. And T1D, the upper limit for T1D is the proton T1. But then once you generate it, you can also use it for ADRF CP. And the matching conditions here are a bit different than Hartmann-Hahn CP. They would be to the matching conditions would be to the local dipolar fields of the protons. And the advantage of that is that, first of all, these matching conditions are very broad, so they're pretty flexible and forgiving. And also they're significantly lower power compared to Hartmann-Hahn CP. So this is the type of sequence that we came up, and that's the sequence we termed PROSPER. And then following this ADRF, the generation of dipolar order, then we have this type of loop CP. So I'll show here what happens in this type of loop CP. So first of all, we have this X nuclei and then these two distinct pools of protons. So we start by doing this frequency selective CP, and then we essentially deplete the dipolar order on the coupled pool. And then following that, actually, I mean, it happens at the same time, but we have here also a delay here, tau. And then during this delay, the dipolar order of the coupled pool is replenished by the abundant distant pool, and at the same time, the X magnetization dephases. So then we basically return to the same point, and we can repeat it n times. And following that, we perform a remagnetization pulse, and then we read out what was left from the dipolar order. So we can see, according to the sequence, that we would benefit from long T1Ds. The longer our T1D, the more we can repeat it, and the more we can deplete the dipolar order on the protons. So here, our first test case was cisplatins. So here on the left, we see these Z spectra that I was talking about, and on the right are the process spectra, and we compared them to optimize broadband acquisitions of brain CP. And so first of all, if we go back to what I said earlier, we see that the depletion of the signal on the proton is indeed proportional to the spectral intensity of the X nuclei. We see here that especially for nitrogen, for N14, we do get enhancement from this method. And also a nice, very nice feature that we encountered is that we were able to acquire over 1 megahertz in frequency with a probe tuned to a single frequency on the X channel. And usually for the brain CP, we had to acquire it at 7 or 8 different offsets. And another compound that we checked was ammonium sulfate. And here we got even more significant SNR enhancements. And also we can see here that in analogy to CES, for those of you who know it, we do have on the expense of the SNR gains, we also have some line broadening. And this line broadening in phosphor is due to the broad matching conditions of ADR-FCP that I mentioned, and also the RF amplitude that we use on the X channel. And here it was very remarkable. We even managed to measure oxygen at natural abundance in ammonium sulfate, as well as sulfur. Both are very low natural abundance. We saw here that we got relatively narrow satellite transitions. And we were wondering, can we use these dramatic SNR gains to measure the satellite transitions at natural abundance if we can perhaps gain some new insights by doing this? So we started by measuring sulfur, and indeed we saw that above here we see the phosphor measurement, and below the compared optimized brain CPU or CPMG, and we saw that we indeed could measure the satellite transitions in only 40 minutes. The enhancement was very significant. It was even hard for us to quantify how much it is because we couldn't even observe the satellite transitions in the regular measurement. I would like to say that it does require good probe stability because of the low signal of the satellites here. So we had to acquire a reference measurement for each point here. So once we got these satellite measurements, we were wondering, what can we learn? Can we learn something new from it? So it turns out that ammonium sulfate is quite an interesting material. It undergoes a phase transition at 50 Celsius or 223 Kelvin. And then it turns from paraelectric to ferroelectric. And so here it kind of changes its structure below minus 50 Celsius degrees. Ferroelectric, it's similar to ferromagnetic, except with electric polarization. And there's been actually quite a long debate about the mechanism of this phase transition, if it was the ammonium ion or the sulfate ion, which is responsible for this type of phase transition. And here we see a nice paper where they measured the N14 single crystal as a function of temperature. So here in the y-axis is the resonance frequency, and in the x-axis we see the temperature, and we see that as a function of temperature, especially these 4 peaks of the single crystal, they change their position, and the CQ increases, and then below the phase transition, this is the critical temperature. So below there's an abrupt change. And then we were wondering if we could get a similar measurement for sulfur in NMR because it hasn't been done so far. So we also grew a single crystal, and we managed to measure a single crystal pretty rapidly. This is with phosphor measurement, and then we gradually reduced the temperature. And we saw here that the satellites are much more sensitive to the change, and central transition, the change is too small to observe. And then minus 52 degrees, we saw actually something interesting. So the peaks here, it looks like they still belong to the paraelectric phase, but here it looks like there's some kind of new phase. And we think this happened because there was some kind of temperature gradient in our sample. And then when we cooled the sample further, we saw that the ferroelectric phase was formed. So then if we plotted in a similar way to the previous slide, we saw that there's, again, here in a similar fashion, there's a gradual change in the CQ that we see from the satellites, and then an abrupt change below the phase transition, which is marked here by the black line. And when we fitted all these spectra, we can see, but phosphor allowed us to see that there's a gradual change in CQ and then an abrupt change. And this agrees with some DFT calculations that we ran. And additionally, we also saw some broadening of the satellites by phosphor, and we think that maybe it's got something to do with the loss of inversion center in the structure. And so at least from these measurements, we can see that both the ammonium and sulfate groups change simultaneously in a very similar fashion. And I'd like to emphasize here that all these spectra are measured in 7 to 20 minutes only, and they span over 800 kilohertz. And depending on the proton T1. And if you recall, I said earlier that we need very long T1Ds, and we saw here that even below the critical temperature, when the T1Ds were only 160 milliseconds, we still were able to measure very good signals. So that's very promising for us in terms of the broad applicability of this method. So if we go back to trying to estimate the SNR enhancement, I measured, in comparison to the phosphor, I measured an ADRF-CP spectrum at an offset of 300 kilohertz in orange here. And according to this, this gives us a lower estimate for the SNR enhancement of a factor of 10. But this is actually an unfair comparison for us, because the only reason I knew that the satellite transition was here was because I previously measured it by phosphor. So if I would actually have to sweep all the frequencies and then get sufficient SNR, I think a fair estimate of SNR per unit time would be at least 100. So then also, we wanted to see if we can also get a similar information on oxygen, and this is the powder sample. This is not a single crystal. And we measured this at 2 different offsets. And according to the satellites, we estimated the CQs at about 5.5 megahertz, and they appear to be high eta. This is in partial agreement with some DFT calculations. And we're looking forward to trying to measure the oxygen down to the critical temperature and see if it correlates to the hydrogen bond changes in this material. And finally, I would like to present a new idea that we had. So if we go back to the single crystals, then this is the N14 single crystal that we grew. And initially, we weren't sure if these are single crystals or if they're single crystals or not. And then we wanted to be able to correlate each satellite transition to its symmetric satellite transition. So we came up with this. This is essentially the same sequence, phosphor, but you radiate at each CP step, you radiate at 2 frequencies at the same time. So one frequency is kept constant, and then the other frequency we sweep in the same way that we do with a regular phosphor experiment. So initially what we got was, this was the raw data that we got for this single crystal. But then when we plotted the same data as a difference experiment, suddenly we got some correlations out of it. So the reference experiment, so in this difference experiment, the reference is the regular phosphor experiment. And the measurement is the phosphor that we did at 2 different frequencies. So what we got here is actually a correlation of each peak here. Actually, it correlates to all the other 8 peaks in the single crystal. And initially, we were surprised by that. But then we realized that whenever we irradiate 2 different frequencies that address the same protons in the unit cell, essentially, it reduces the signal. So the correlation is actually to all of the other peaks that are in the same unit cell. So for this single crystal, it might not be the most useful, but then let's say we have 2 single crystals, maybe that can help tell them apart. And we're also excited to maybe use this for heteronuclear correlations, maybe be able to correlate nitrogen and oxygen, or even sulfur and oxygen, which is virtually impossible otherwise. So just to conclude, I showed you that phosphor leads to significant signal enhancements in static samples and enables the detection of oxygen and sulfur at natural abundance. And remarkably, we were also able to measure the satellite transitions, even for short T1Ds. We were able to follow the sulfur satellite transitions and study the phase transition of ammonium sulfate from the sulfur point of view. And then I also showed you 2D N14 correlation experiment based on the proton saturation in the unit cell, and this is still ongoing work. We're looking forward to test it as heteronuclear experiments. And finally, I'd like to thank my group. I'd like to thank you for listening, especially Michael Drasovic and my advisor, Lucio Friedman, for his constant support.
Thanks, Tamar. Yeah, please.
Really nice talk and exciting work. I have a question on this. Can you comment on the adaptation of these schemes in magic angle spinning?
That's a good point. That's actually something that we want to look into. So there has been some work on the problem is that when you start spinning, then you average some of your dipolar interactions, which help generate the dipolar order. There has been some work on generation of dipolar order under magic angle spinning. They term it second order dipolar order. And that's something we want to look into about implementing this sequence under spinning. That's definitely something interesting for us.
Yeah, yeah. The follow-up question is, so you're already showing like significant defacings, even when natural abundance, oxygen, sulfur, and all of that. But can you comment on what's the limiting factor that limits the overall absolute defacing of the proton signals that you're observing? Like, could you get further maximal absolute defacing, if that makes sense?
Can you repeat, what is the overall factor that is limiting what?
The absolute defacing of your proton signals.
What is the limiting factor of using this sequence? If I understand your question correctly, I think the overall factor that is limiting us is the T1D, which is in turn limited by the proton T1. So the upper limit for the T1 of the dipolar order is the absolute T1, and then the T1D limits the number of your signal enhancement, essentially.
Right. Okay. Thanks.
Great talk. This is really exciting. This is the first time I've heard of T1D. How do you generally measure that? What is that? Can you explain a little more on that?
Yeah, that's a good question. So T1D essentially would be the equivalent of T1, but it's the time scale that determines how long your dipolar order lives. So the way I would measure it is like if we, we can, even this sequence is good. The way I would measure it is it's kind of similar as a saturation recovery, but I would generate the dipolar order, then I would kind of gradually increase tau, and then I would remagnetize and measure it again and see how much is left. So the decay would look kind of similar like a T2 decay, depending on your different delays. And that's how I would measure it.
Okay, makes sense. I had a second question, which is, so this is a frequency sweep experiment. Do you have a robot on the Met? Are you there turning the thing as you go in each one? Or is it like, so do you have to retune the probe, I guess, on the other channel is the idea? Or are you just changing the frequency? So actually, by frequency, you mean that I'm doing each experiment in a different frequency. So I just set up an array on the instrument. It's pretty. But you don't have to retune the probe or anything. No, yeah, that's actually the big advantage that for each of the experiment I showed, I was tuning it at a single frequency. So for the sulfur and oxygen, it was tuned in the central transition, and then you can see that the band. I mean, I can still see signal a megahertz away. Yeah, they're all tuned at a single frequency. Very cool. Thank you.
A brief follow-up on that. How do you know how wide your window has to be? Is that specified?
How wide the what?
How wide the window of, in other words, that you have to sweep? Do you know a priori? Or
yeah, so it depends on the compound. I mean, for the oxygen, I didn't know in advance, so I just tried different offsets, and I saw until when I see the signal decay. But if you have an idea about your CQ, you know roughly where it should be. But for the oxygen, I didn't know actually.
All right, with that, let's thank Tamar for a really nice, exciting talk. I'm delighted to welcome Mariano Sardo from University of Aveiro in Portugal.
Okay, good afternoon, everyone. I'm feeling specifically small here, but as long as you can hear me, it's not important that you can see me. So I'm very excited to be here to talk to you a little bit about what we have been working in my group related to the CO2 speciation in amine-based solid adsorbents, and we use the solid-state NMR to study it. Just to start, I just want to show you where I come from. I come from Portugal, more specifically the University of Aveiro. And besides having a beautiful campus, please visit if you have the chance. It is the #1 university for material science in our country. So today, this is the outline of my presentation. I will start by giving you a brief overview of why we are doing what we are doing, so the motivation. I will present to you the materials that we have chosen to work with, the amine-modified porous silicas. I will give you a brief highlight of some previous works to give you the context of what I am going to show you. I will also explain the methodology, how we do it, And finally, I will reach to what is really the effect of moisture in this CO2 speciation mechanism. So starting by the motivation, I think everyone is aware about the current challenges nowadays concerning global warming and climate change, and also the urgent need to try to mitigate CO2 emissions from large point sources. And in this case, CO2 is one of the major culprits, as you can see in this pie chart here, which CO2 is the gas that contributes more for the global greenhouse gas emissions. So there is a high demand to try to capture and reduce these CO2 levels. Currently, as far as CO2 capture technology is concerned, there are three main technologies, and from which I'm going to talk about the post-combustion CO2 capture, because it's one of the, it is easily retrofitted to existing power plants, and this is where I'm going to be focused on in my presentation today. So the basis of this capture technology is the adsorbent. And from several decades, one of the main technologies, the benchmark technology, has been amine solutions. But they present some drawbacks, including some toxicity and also some high regeneration energy requirements. So for that reason, solid adsorbents have been pursued to try to be alternative adsorbents for the CO2 capture. What do they need to present? So they need, specifically, again, for the post-combustion CO2 capture process, they need to operate at a relatively low temperature, they need to be stable towards moisture, and they also need to operate at low CO2 pressures. Among many possible candidates, amine modified porous sorbents are potentially good candidates. And why? First of all, they have pores that are wide enough for the application that we want, and also they are highly tunable, which means that you can tailor their chemistry, tailor the number, the nature, and the size of the nitrogen atoms that you insert into your material. So you can see here that you can change not only the nature and the size of your amines, but also the way you insert those amines into the material. And here I just show you, you can either functionalize, which is represented here by this bond and this R, which has lots of possibilities, primary, secondary, tertiary amines, and all of that. And also you can also impregnate your amine into your system. But before I go into the topic of my talk today, which is this one here represented in blue, the effect of moisture in the CO2 speciation, I would like to give you a brief overview of what we have been doing from a couple of years back, giving you three highlights of that work. And it all started with this two benchmark papers in which our group has characterized three chemisorbed CO2 species. For that, we have done several 1D, 2D experiments. We have also played a little bit with the isotope exchange to confirm some of our assignments. And obviously, we have performed molecular modeling to be sure that that our hypothesis made sense, and to also confirm the assignments that we have done in the NMR spectra. And this was actually this paper from 2011 was the first experimental evidence of the carbamic acid moiety in solid adsorbents. And this way, we were able to give an atomic level insight on the CO2 speciation of chemisorbed species formed in the surface, at the surface of silicas. So after we have characterized these chemisorbed species, we have also noticed that there is a link between the nature of the amines and some cooperativity effects in the amines. So the distance of the amines inside the material influences the nature of the species that are formed. And so we have tried to synthesize, which is represented here, we have tried to synthesize materials in which we have different distances between the amines. And for that, we have inserted a spacer. So basically, we force the amines to be separated, and we increase the amount of isolated amines, and vice versa. So we have different types of materials with different types of interamine distances between them, and this way we can correlate that. We know that the intensity of these chemisorbed species is nicely modulated by this amine coverage. And in this particular paper, we have also benefited from carbon chemical shift anisotropy to be able to distinguish between neutral and protonated species. And finally, the work I want to show you before I go into what I really want to explain to you today, and this work, you can also see it in poster 161. Please do visit us. We have here Ildefonso and Luigi as well. We are more than happy to discuss it with you. So in the previous works I've shown you, we have focused on the chemisorb portion of the species that are formed. However, the physisorb species usually dominate the spectra. And in this particular work, we have tried to not only quantify, but also characterize the physisorption. And it is more difficult because, as you can see, at least this is the chemisorption portion, and you can see that the chemical shifts are slightly different. But as you observe the physisorb portion, you see that they fall in the exact same chemical shift. So how can we disentangle if we have one species or more than one? So for that, we have performed numerous experiments that you can see detailed in the poster, but here I'll just quickly show that here. So if you look at the saturation recovery curve, you can more or less see that we observe by the measurement of the T1 values, we observe 3 different physisorb species. So now that I've shown you, we have characterized the chemisorbed, physisorbed, and now we will look into water. Why will we introduce water in the system? As you know, water is ubiquitous in any gas mixture, and it's very important. In real life applications, you for sure will have CO2 mixed with water and even with other components. So this is why we decided to pursue this study. Before that, I will just show you what is transversal to all the works I have shown you, and which is pivotal for being able to have these results, which is the way we pack the rotor. So basically, we have set up and we have improved it over the years with our experience. We have a vacuum line, so we have built a glass cell that I will show you how it looks like in real life in my next slide. You have here on the bottom an NMR rotor. You kind of glue stick the cap here, and this goes up and down, so you are able to close the rotor. And then you connect this NMR cell to your vacuum line. And so you can vacuum, you can mix CO2, you can put helium, you can put whatever gas you want, and you can even put water vapor, which is what I did in this particular work. So this is how it looks like. This is the top part where you put the cap right here. You can go to the next one. So this is the cap of the rotor. This is a 4mm rotor, and this is the bottom part. And this one you can adapt. You can put a 4mm, a 7mm. You can build whatever you want. And basically, once it is closed and connected to the vacuum line, you can admit whatever you want and then close your rotor in controlled temperature and pressure conditions, which is really crucial for our results. And this is how it looks like. So the cell is here. Here we have the pump, and here we have the CO2 bottle, helium, and yes, here is the water reservoir. So starting with the effect of moisture in primary amines. If you look at the adsorption isotherm, you can see that there is no significant change between the adsorption capacity under dry or moist conditions. However, there were some debates in the literature saying that probably there should be an increase in CO2 uptake induced by water. So once the material is exposed to water, it absorbs much more CO2. And that mechanism was believed to be based on the formation of a bicarbonate. If you look at the stoichiometry, here is 0.5 and here it's 1. But if we observe our NMR spectra, and these are carbon quantitative NMR, okay? If you look at the dry, under dry conditions, and one of the reasons, let me go back a little bit, one of the reasons why it is so important to pack the rotor in a controlled atmosphere is that this species over here, that we call A, even with the slightest amount of water, 0.5 torrs, it really disappears. So if you don't do it in these conditions, you will never catch it, you will never observe it. And if you look at this spectra compared to the one under wet conditions, and in this case we used 0.5 torrs of water, you can see that species A converts into species B, and species B converts into species C, which is represented here in red. I will, in the next slide, show you this in more detail. So the question remains, is either of these species bicarbonate? How can we be sure? If you compare, this is an overlay of a tertiary amine with the exact same material, the SBA15, and you can see here with distinct amounts of CO2, you can see that there is a species formed at 161. Why do we compare the primary amine with the tertiary amine? Because in tertiary amine, you only have the formation of bicarbonate. There is no other species. So our hypothesis is not that the increase is due to bicarbonate. The alternative mechanism that we propose is that the carbamic acid converts into carbamate because water promotes a proton transfer from the carbamic acid to the carbamate. And obviously we have performed modeling on the structures to be able to confirm our hypothesis. And as you can see, when species A becomes in contact with water, it forms hydrogen bonded carbamic acid species, which is this one here that we call A prime, and species B converts to species C. And as you can see here, this chemical shift, which was this one here, when it's hydrogen bonded, it goes to 161. And here as well, you can see that depending on if this carbon is under dry or wet environment, you can see that they fall into more or less the red part here. And if you compare the Gibbs energy difference, you can also see that under wet conditions, the most stable species is ammonium carbamate and not bicarbonate. Now going to tertiary amines, here we can see that there is a change in the absorbed amounts of CO2, either if you are in dry or in wet conditions. And we have here the dry in purple, we have a tiny amount of water and a little bit more water in blue. So as you increase the water content, you also increase the amount of CO2 absorbed. And here in this case, if you look at the NMR, it's again quantitative NMR data. If there is no water in the system, so if you just absorb CO2, you see that there is a very weak peak. Well, not so weak, but there's a weak peak. You see that there's a lot of noise at around 155, which can be maybe attributed to a carbamic acid-like species. The calculated chemical shift fits very well with our experimental data. And as long as you start putting a little bit of water, you start seeing the 161 peak coming up, which increases when you increase the water content, and that one is attributed to bicarbonate. We have also looked to see if we have some kind of species like this, where the N connects, establishes a bond directly with the carbon, but that would have to appear at 141, considering the calculations, and we haven't seen that in the spectra, in the experimental data. And so now, just to finish off my presentation, I've shown you what we did with pure CO2, what we did with CO2 and water, and now we have done a three-component mixture. So we have observed what happens to a mixture of CO2 and methane when you have water. What happens to the selectivity of the material? And you can see that changing the nature of the amine changes dramatically, because, for instance, for the primary amine, there is no significant effect on the selectivity towards CO2. Under wet or dry conditions, it's more or less the same. But if you go to the tertiary amine, there is a huge difference. And so the selectivity increases with moisture, possibly due to the formation of bicarbonate. So, and finally, I just like to thank all of our team. Obviously, some of the work, it wasn't me who did it directly, because I entered a little bit later. But we have been fortunate enough to be funded for the last 5 years by the National Portuguese Science Foundation, and also by the European Research Council, with a consolidated grant to Luís Mafra, which is our group leader, and that has been given us a lot of tools that we have been able to expand our team, expand our equipment, and we have been doing a lot of interesting stuff that I hope we can present to you in the future. I'll just leave you with a little bit of about the timeline of our papers if you want to QR code them, but please do come talk to us. There are 3 of us here, and we are more than happy to answer your questions. Thank you.
Questions for Mariana?
Not a question, just a better seat.
Not at all. So, of course, we too work in this area.
Yes,
and so
it's an honor that you are my chairperson.
Not at all. So we've actually found that under CP, of course, it favors the carbamate species, but the dynamic averaging of bicarbonate because of the water present. So have you found that your aptus systems seem to be just a little bit different? And so
yes.
Does it show up, or have you tried those direct detection experiments?
Yes, we've tried, but we have never been able to detect the bicarbonate. No.
It's amazing.
But yes, we have done the direct, obviously.
Yeah, the
and we even done the quantitative NMR, CP. Yes.
Yes.
Yeah. So I'm not familiar to this field, but sounds like your study also can be compared with vibrational spectroscopy results, like IR or Raman spectroscopy. Is there any consistency or advantage, disadvantage?
Well, I think, let me see if I understand your question. So you're saying that we can also study this by vibrational spectroscopy, and if there is any advantage of using NMR or vibrational spectroscopy.
Yes.
Yes. For many years, you have been studying these solid adsorbents with vibrational spectroscopy. The problem is that sometimes you have overlapping bands, and you cannot really distinguish, because it's like carbamate and carbamic acid, and they sometimes, depending on the nature of the material, they fall into the same wave number. And then it's easy. That's why sometimes you have misleading assignments in the literature. And I think NMR, solid state NMR, is much more powerful in that.
Better. I see. Thank you very much.
Welcome.
Very nice talk. Are you guys looking into 15N labeling on your amines?
Yes. It's on the future plan. Yes.
Do you expect to see anything quite interesting? I mean, any conformational changes in the amines, things like that? Just comments, any idea?
I don't know, but I think it will be very important to look into the oxygen, into the nitrogen 15, and also on the oxygen, by the way. It's part of the ERC plan of Luís to be able to label the amines with the nitrogen 15, obviously. And I think it will open up, you can see, because everything is happening not only around the carbon that forms the carbamate or the given species, but also around the nitrogen of the amine. I'm not sure if I answer your question.
No.
In terms of.
Perfect. Thank you.
Okay, yes.
Great. Well, in the interest of time, thank you so much for the talk, Mariana. So let's give her a hand. ASIF Iqbal is next from UC Santa Barbara.
Is it? The time is? Oh, okay. So first of all, thank you organizers. I'm very excited to be talking about my work. So today I'm going to tell you about how we can tailor electron-electron coupling network in order to improve DNP at high magnetic field and fast MAS. This is very important experimental condition to have both sensitivity as well as resolution. In this talk, I'll be focusing on nuances of these mechanisms in the high field regime. DNP mechanisms can be broadly classified either as a flip-flop mechanism or a triple flip mechanism. So in flip-flop mechanism, we have a simultaneous flip of one electron and a nucleus. It could be through cross-relaxation in the case of Overhauser DNP, or it could be microwave-driven for solid effect DNP. In triple flip, we have three simultaneous flip of two electrons and a nucleus under a certain resonance condition. And the good thing about this kind of mechanism is that it's intrinsic to the system. So the interaction that is required is already present. Triple flip mechanism can be broadly classified as cross effect and thermal mixing DNP. They are very similar. The difference comes in terms of the broadening of the EPR line width. If the EPR is more inhomogeneously broadened, then it's cross effect. Otherwise, it is defined as thermal mixing DNP. In order to maximize DNP transfer from electron to the nucleus, what we need to do is tune our local and global electron spin concentration. So if I have to give you a model, suppose you have 6 electrons and all 6 of them are isolated, then it would only be either solid effect or Overhauser effect that would be operative, but will not have cross effect. On the other hand, if all of them are coupled, then we will have a lot of cross effect or thermal mixing resonances present. So it seems like a coupled electron spin system is a better choice in order to have improved DNP. Within the coupled electron spin system, we can have a biradical system or multi-coupled electron system. The biradical is easy to design and manipulate, but we can also have something good efficient DNP coming out of multi-coupled electron spin system. In my talk, I'll focus on these two systems. First, I'll start with biradical, for which we make use of cross effect mechanism, the standard cross effect mechanism. The important thing about cross effect, the most important thing about cross effect is that we need to generate a large polarization difference between the two electrons. So this is the crux of cross effect mechanism. Under MAS, the things are a bit more complicated because the electrons' energy, they are modulating because of rotation. But here too, the crux is whenever we have this cross effect resonance satisfied, we should have a large polarization difference between the two electrons. In last 10-15 years, a lot of different radicals have been synthesized, and along the process, we now have a better understanding of what should be the spin parameters which should lead to efficient cross effect DNP, what should be the relaxation or G tensor. The one parameter that I'm going to focus in this talk is electron coupling network. So for example, I will, as an example, I will take amipole and comparison between amipole and tiny pole and show how the DNP or how the coupling should be tailored in order to have a good DNP. So amipole, we all are aware of, it's a gold standard radical, especially at 400 megahertz of DNP. But if we see its performance at higher magnetic field, the performance dramatically decreases. And The factor or this is attributed to this factor, the cross effect rate, which is scaled down by the Larmor frequency of the nucleus. So say proton here. So if we want to have better cross effect at higher magnetic field, the solution can come from this rate itself, that we should increase the coupling such that the cross effect rate remains high even at higher magnetic field. And this concept was utilized in the synthesis of tiny pole, which is very similar to amipole, but the linker size is smaller, which leads to a stronger dipolar coupling of 50 megahertz. If we compare the performance of tiny pole and amipole, tiny pole is definitely better at higher magnetic field, but the overall sensitivity is still far below the theoretical maximum of 660. So it seems other than having like strong dipolar coupling, there is some other factors. In our analysis of tiny pole, we found that that factor is basically a balance which needs to be maintained between the dipolar coupling and scalar coupling. If we look at tiny poles, the molecule is very flexible, so it has a distribution of J coupling. The most probable distribution of tiny pole, it has J coupling. Accidentally, it has J coupling, which is not optimum. And by optimum, I mean the ratio of J coupling and dipolar coupling is less than 1 in tiny pole. And such orientation where the ratio of J and dipolar is less than 1, they lead to inefficient DNP because of interference between dipolar and J coupling. Dipolar coupling, you all know, is anisotropic, so it can have both positive and negative value, but J coupling is scalar. So it may happen that for certain orientation, we are having effectively very small coupling. And all those orientations, they lead to very poor DNP. And why we want effective electron-electron coupling, strong electron-electron coupling, it's not just to maximize the cross effect rate or the CE rate that I showed you in previous slide. It's rather to maintain a large polarization difference between the two electrons. So if we look at these energy pictures of the two electrons, there are points where the two energies of the electron, they become same. So if at those conditions, if the coupling is weak, then there would be something undesirable which will happen, which is the polarization difference between the two electrons would not be maintained. So I'm trying to show here a picture of what should be the crossing. So if we have, say, this crossing here, the coupling has to be large in order for the transfer of, or the exchange of polarization to be adiabatic. So if it is strong coupling, we'll have 100% swap of polarization, but if it is weak coupling, then we'll have a diabatic transition where the polarization difference would be smaller. So in order to have a good cross effect DNP, we need to have a ratio of J and dipolar coupling which is above 1, so that we don't hit this non-adiabatic condition. With this understanding about what should be the coupling between two electrons for cross-effect DNP, we have a recommendation on improving DNP at higher magnetic field. And the recommendation is that we need to tailor our electron-electron coupling tailored to the external magnetic field. So if we have, for example, if we are doing DNP at 400 megahertz, the DNP, the coupling should be weaker. It should be roughly 1/10 of the Larmor frequency. So the coupling should be roughly, net coupling should be roughly 40 megahertz. And out of that, the 2/3 of the contribution should come from J coupling. So, and if we are going to higher magnetic field, for example, at 1 gigahertz, the coupling has to become stronger, but the balance between J and dipolar coupling has to be maintained. So if we follow these two constraints, then it's possible to have effective cross-effect DNP even at very high magnetic field of 1.2 gigahertz. But the caution that I would like to mention is the coupling should not become too large. If it becomes too large, then we reduce the polarization difference between the two electrons. So this was the first part of my talk, where I focused just on the intramolecular coupling in order to maximize the cross effect. Many times when we do DNP experiments, we run at a sample concentration where the intermolecular interaction cannot be avoided. And if we have to make a guess, we would say, oh, if these interactions are there, then the relaxation of electrons would become very fast and we may end up having a lower DNP. But this in general is not true. In general, we always have an interplay of microwave power, which is leading to saturation of the electron spins. And then we have spectral diffusion. That saturation effect is transferred across the EPR spectrum. And we also have relaxation of electrons. So in general, it's the interplay of these parameters that determine whether or not the DNP would be efficient. It's hard to monitor the effect of spectral diffusion if we are working with nitro oxide kind of radical, because the EPR line is very broad and all the different DNP mechanisms, they are overlapping. But it's possible to make use of narrow line radical and see the effect of intermolecular coupling. So in our study, we made use of a trital, which is a narrow line. And if the trital is too diluted, then we would only have solid effect enhancement for the trital. It could be a zero quantum or double quantum solid effect DNP. But if we have concentrated trital, as we increase the concentration in trital, what we see is apart from having solid effect, we have DNP coming right at the center of the trital. So, and this we didn't have any other option. What could this be? So we assigned this to be thermal mixing DNP. And we see, like, as we increase the concentration, this thermal mixing DNP in trital, it enhances and the solid effect goes down. The important thing about this finding is that the amount of microwave power that we require in order to achieve efficient thermal mixing DNP, it's much lower than what we would require for solid effect. And so which means that we can do DNP with low cost microwave synthesizer. And this is very important in order to make DNP very accessible to labs across the world. So this seems very exciting to us. And we can find the signatures of this thermal mixing DNP using EPR, something that I'll show you later in my presentation. But now we would move to another radical system, which is BDPA. BDPA has remained a very mysterious polarizing agent right from its synthesis. Like, it took almost 25 years for this radical to be synthesized and published. So it has a mystery associated with it. The mystery with BDPA in the context of DNP is that if we look at BDPA, it's a narrow line radical. So it should only give this solid effect. But Griffin and many others now have found that in BDPA, if we run a complete DNP profile other than solid effect, we have this positive DNP enhancement. And what is even more exciting is that the amount of microwave power that is required to get the maximum DNP in this system is very minimal. And very recently, it was shown that selective deuteration of some of the protons, especially those which are strongly coupled, that can change the DNP profile from a positive DNP to negative DNP. And with all these finding, the BDPA, this central DNP enhancement profile has been assigned to Overhauser DNP. So this is a very carefully performed experiment with carefully designed molecule, but there is a problem, and that problem is the features that we have associated to the Overhauser DNP in BDPA. These features are very common even for cross-effect DNP. For instance, the central peak that we see here, it's assigned to Overhauser, but this central enhancement is possible even through cross-effect between a slow relaxing and fast relaxing radical. So, for example, couple of years ago, we found that trital gives the central DNP enhancement when it in cross effect with a fast relaxing tempo. The other thing is the power requirement. In Overhauser effect, it's thought that the saturation is allowed single quantum transition, so the power requirement is low. But if we closely look at this power profile, after reaching a maximum, the enhancement starts going down. So this cannot be a feature of Overhauser effect. If it is Overhauser saturation, then the it should reach a maximum and remain a flat line. But here we see the enhancement starts going down as we increase the microwave power. This, on the other hand, can be an attribute of cross-effect DNP. If we have two electrons, and in cross-effect, since we need to maximize the polarization difference, a microwave power above optimum would lower the polarization difference, because then we would start saturating both the electrons. We won't be saturating selectively at very high microwave power. So this decrease in the DNP enhancement with microwave power, large microwave power, could be an attribute of cross effect. And the third point that I want to make here is about deuteration effect. So very recently, Ravi, Shankar, and few others from Griffin's lab, they showed that the profile changes on deuteration, and the rationality associated with it is, if we remove these closely associated protons with deuterium, then we would like change the dominant relaxation mechanism from zero quantum cross relaxation in the case of fully deuterated to double quantum cross relaxation in case of selectively deuterated. So this could be true, but then we also know that deuteration can change the spin relaxation, or T1e of the electrons. And if T1e of the electrons are changing, then the saturation profile of the electron, when we put microwave on our system, that can also change, and that can change the DNP profile. This is something that we first numerically showed last to last year, that the DNP profile for a clustered system could be positive, it could be negative, or it could be dispersive. And very recently, a PhD student in Sanghi Han's lab, she showed experimentally that indeed, for the same radical system, BDPA, it's possible to switch the DNP profile from, say, absorptive to dispersive. And also, very recently, Prisoner and co-workers, they have shown BDPA, when dispersed in lipid, it gives rise to a thermal mixing profile. So it's a dispersive DNP profile in the center. So all these things that I am showing you, which I have shown you right now, it's all based on NMR detection. It does not mean we can just infer about what might be happening to electrons, but we do not know exactly from these profiles. In order to understand what might be happening to the electron spins, we did some EPR measurements of these radical system. It was possible through an DNP instrument, which could also do EPR detection at the same condition. In our EPR measurement, we found that the radical system, which gives rise to thermal mixing DNP, it has an asymmetric profile, and that's needed in order to generate a polarization difference. What is even more interesting in our EPR finding is that the systems that give rise to thermal mixing DNP, when we perform Eldor experiment, which is a pump probe experiment, where we first saturate a portion of the EPR line and see how that saturation affects a certain select probe frequency. We found that for systems which gives rise to thermal mixing, we have these humps. Normally, we would have expected only a saturation or the flat line, but here we have these humps coming up in systems that give rise to thermal mixing DNP. From simple analysis based on product operators, we associate these hyperpolarizations or humps to be coming out of dipolar order. So if we look at the density matrix of Zeeman order and dipolar order, we can interconvert Zeeman order and dipolar order by selectively flipping a spin manifold. For example, if you flip this manifold, we go from Zeeman order to dipolar order. And in this numerically simulated spectrum, you can see for a coupled spin system, if we do a selective saturation, then we saturate the Zeeman order, but simultaneously we are creating the dipolar order or two spin order. And if we saturate with higher microwave power, the two humps, they get more separated, but it's created. So selective saturation can lead to the creation of two spin order or dipolar order. Our experiment is something like this, where we first pump, then we have delay, and then we probe. So basically, if we can have this schematic where we have Zeeman order, and then with pump, we are creating the dipolar order, During this delay, there can be different relaxation dynamics of the Zeeman order and dipolar order. And with probe, we convert these orders into coherents, which would be in phase and out of phase. So by controlling the spin parameter, it's possible to change the relative amount of saturation or the Zeeman order and the dipolar order, something which we could confirm experimentally. So these experiments shows that the state of the electron spins is in fact coming out to be like a clustered state in the case of Brightel, and something which we also see in BDPA, which gave rise to, in our opinion, thermal mixing DNP, where we have these strong humps coming up in the BDPA experiments, in BDPA EPR experiments. So, and it could be because like in BDPA, we have these biphenyl rings, which could lead to stacking of different BDPA molecule. So with that, I will like to conclude. I hope I showed you that in cross effects, it's possible to have high enhancement even at 1 gigahertz or larger magnetic field if we tailor the inter-electron coupling. And we have shown that it's possible to have thermal mixing DNP for clustered system. And this seems to be the case in the case of Trital and for BDPA. And moving forward, I think it would be important to explore thermal mixing DNP furthermore under MAS condition using controlled microwave radiation and using controlled spin parameters. With that, I would like to acknowledge people who have helped me these experiments or were part of this experiment, and especially Songi Han, who is my PI, and she was very supportive. At the end, I would like to briefly mention about this global NMR Twitter conference that we are going to have very soon. It would be open for all students and postdocs. It's being sponsored by SMAR, so I recommend that all of you participate. Thank you very much for your time.
That was quite a tour de force. Yeah, please, just a couple of brief questions. Yes, in the interest of time. Thanks.
Yeah, ASIF, nice talk. One of the questions I had is you showed that microwave power dependence of the BDPA enhancement, right? That the enhancement decreases with increasing powers. Couldn't that potentially be explained by increasing temperatures? Can you comment on that?
It's not temperature, because if it is temperature, then all the say solid effect would also go down with higher microwave power. But solid effect increases. It's only the central DNP profile that decreases with higher microwave power. So it's not temperature.
Oh, I see. Okay, so you're not showing that, but you have indeed observed that it goes up. But I mean, there has got to be some sort of compensation, right? So between the absolute gain and enhancement you get with the solid effect, maybe we don't see as much as we are supposed to see, if that makes sense.
I think in solid effect, if it is temperature rising up, solid effect is more prone to relaxation. Like for solid effect to be efficient, relaxation should be longer. So if temperature is rising and relaxation is becoming faster, solid effect would go down dramatically faster than say thermal mixing DNP. So we think it's not solid effect. It's not temperature dependent thing.
Okay, thank you.
Yeah, George.
Yes, nice talk. Just wanted to know, so you're giving a recommendation which is to increase the J coupling for efficient DMP at high magnetic fields, let's say around 1 gigahertz or so. But so we've seen, for example, that it's really critical to the number of bonds between two nitroxides or just a BDPA and nitroxides. For example, if you have 2 bonds, could be too short, too strong coupling, 3 bonds, too weak coupling. So, I mean, what modifications would you suggest in terms of synthesis to achieve that?
I think, it's very hard to suggest what exact chemical modification would be required, but DFT might be a good approach. Like first doing some DFT calculation on the molecule and then synthesizing them, because I know there have been like over hundreds, 200 of molecule biradical, but only a few of them work. It could be that we are not, when it's synthesized, it does not have the optimum parameters.
Well, let's thank ASIF. So there was so much in that talk, so we'll have to come again. Always something new with DNP, so it's great to hear. Matthias Eden is our last speaker from Stockholm University.
Thanks. Let me start by thanking the organizers for giving me the opportunity to present our work. Well, the title of my talk is Biomolecular Binding at Calcium Phosphate Surfaces and New NMR Crystallography Methods. And I will start by giving a brief introduction to the systems. Calcium phosphate cements are used as biomedical implants, particularly for filling voids in bone and tooth. And one well-known cement is formed by taking a powder of alpha tricalcium phosphate, mix it with water, and then this paste sets and hardens into a structurally disordered form of hydroxyapatite, which has a similar chemical composition to bone mineral. What I want to talk about today concerns phosphoserine-doped cements. And this is within a project that we have been running with my group, together with the groups of Håkan Enqvist, Håkan Enqvist at Uppsala University, Molly Stevens at Karolinska Institute, and Peter Thompson at University of Gothenburg. And phosphoserine is an ester between serine and phosphoric acid, and many of the proteins believed to control bone mineralizations are rich in phosphorylated serine residues. And now our co-workers at Uppsala has found that if you mix phosphoserine into the cement formulation, then you get a cement that is strongly bone adhesive. So one obvious application for these materials are to glue fractured bone together. Here you get a feeling of the strength of this glue. These are two pieces of cortical bone that are glued together. Each is only of area 1 square centimeter, but as you can see, this can withstand a load of 4 kilo. So by the end of my talk, I hope to have conveyed to you these are complex heterogeneous materials. What are the cement components involved here? And also to answer why are phosphoserine-doped cements bone adhesive when serine-doped ones are not? And then for the most of my talk, I will focus on the organic-inorganic interface. How do the biomolecules bind at the structurally disordered calcium phosphate surface? And towards the end, I will talk also about the new NMR crystallography method we introduced recently. And this has several advantages. It gives rapid validation of, potential model structures with a minimum of both experimental and numerical efforts. You only need to record 1 2D NMR spectrum. There are no numerical simulations involved. And we have applied this to DFT refined structures of phosphoserine and its calcium salt. So here you see phosphorus 31 and proton NMR spectra recorded from polycrystalline phosphoserine and then from cements with increasing phosphoserine contents. And in the cement without any phosphoserine, both NMR spectra are typical for disordered hydroxyapatite. Then if you take a look at the spectra from only using cement with 4 mole% of phosphoserine, you can still see the apatite component. But there are also a set of very sharp NMR peaks forming, and they come from unreacted alpha TCP. Then for larger phosphoserine contents, there is no longer any evidence of apatite, and what rather forms is a very broad resonance that stems from phosphates in amorphous environments, and that goes for organic as well as inorganic ones. So we refer to this cement component as ACP PSER because it consists of a separate phase where amorphous calcium phosphate is intimately integrated with the phosphoserine molecules. And this component is largely responsible for the bone adhesive properties. We have found very good correlations between the amount of the ACP PSER phase and the shear strength experimentally observed from the cements if you take 2 cubes of either bone or steel and glue them together. And in the plot you see here, we have plotted here the ACP PCR content against the batched phosphoserine content in the cement. And the amount here was obtained just by deconvoluting phosphorus 41 NMR spectra. Then you can compare, well, these are the contents of ACP PCR. You can compare the results with the data in red here, which is the corresponding shear strength for the cement. And you can see that the shear strength remains high whenever the ACP PCR content is high. Then we have also analyzed serine-doped cements, and for low serine contents, they work pretty much in the same way. There will be an amorphous ACP phase with serine molecules integrated. The problem is that when you increase the serine content, this phase doesn't develop further, so the TCP and serine just remains unreacted. And that is reflected here, as you can see, in a low shear strength throughout. So the serine-doped cements are not bone adhesive. So we have performed various NMR experiments along with metadynamics MD simulations to try to figure out, well, what is the nature of this ACP PCR phase. And our main conclusions is that it's a fairly homogeneous phase, at least across a 1 nanometer or a nanometer scale. And it involves primarily, along with calcium, protonated phosphate groups. An interesting issue here is that these phosphate groups, it's totally impossible to distinguish them by NMR in terms of organic or inorganic origin. So what the next thing then, yes, how is the cement organization? And here we have proposed a simplified model of the cements, but they consist of micrometer-sized particles of alpha TCP that coexist with this amorphous ACP PCR phase. That's the yellow color here. And that one consists of phosphoserine molecules embedded in ACP. So support for this model is also given here by the scanning electron microscopy image you see here, where a micrometer-sized alpha TCP particle is coated by the amorphous ACP PCR phase. So for the remaining, I will focus on talking about basically the interface between the organic molecules and ACP, and more precisely how the molecules bind at ACP. So what you see here are dipolar-mediated HMQC spectra, proton phosphorus, which were recorded from cements that comprised either 30 mole% of phosphoserine or 36 mole% of serine. And in the case of the serine-doped cements, since there are no organic phosphate groups, the correlation signals here shows unambiguously that you have protons in both aliphatic groups and primarily the amino group that are in close proximity to the phosphate groups of the inorganic phosphate groups of ACP. Then the corresponding spectrum from the phosphoserine-doped cement, well, it's very similar in the proton region associated with the organic protons. In the high ppm region, we see correlations between acidic protons and both organic and inorganic phosphate groups. So what we will take next a look at are the proximities between the carbon-13 sites and the inorganic phosphate groups. And here we obtained powders of uniformly carbon-13 and nitrogen-15 enriched serine and phosphoserine. And we prepared one cement each from those precursors, cements with 16 mole%. Here you see the resulting HMQC spectra. And I would like to comment here that under our experimental conditions, The signals that are detected here, they are from groups that are in close proximity to the inorganic phosphates, but that also includes not only the carbon sites that sits in functional groups directly bonded, but also other groups a little bit further away. This is, for instance, obvious here that we see correlations here between the aliphatic carbons for serine, and we know from phosphorus, sorry, we know from carbon phosphorus redoor experiments as well as MD simulations that there is no aliphatic groups that bind to the surface for either serine or phosphoserine. The same thing goes for the carboxy group of phosphoserine. So the correlation spectrum here, the peak intensities merely reflect the intramolecular contacts with organic phosphate group. For serine, on the other hand, we do see a strong binding at the carboxy site with at the ACP surface. And here you see zoom of the carboxy region. We can identify three groups of peaks, which has quite different dipolar second moments, carbon-13 phosphorus. They are very different among the groups as well. These were obtained from carbon phosphorus redoor NMR. The groups in the middle here, marked by the blue rectangle, those are attributed to carboxy groups that do not bind directly at the surface, as opposed to the other two groups here, which we have made tentative assignments of based on the chemical shifts. So here, for instance, for the peak here at 184 ppm, that one we attribute to carboxy sites that are bound electrostatically to calcium ions at the surface. And those calcium ions are mainly surrounded by non-protonated phosphate groups. The other peak over here, which has a lower chemical shift of 170 ppm, and it also correlates with phosphates with lower phosphorus shifts. This peak here we attribute to hydrogen bonding between the carboxy group and HPO4 groups. So we will next take a look at the potential binding of the amino group at the structurally disordered calcium phosphate surface. So besides for the two cements, we use the isotopically enriched phosphoserine for preparing a model system of nanocrystalline hydroxyapatite that was grown from a solution comprising phosphoserine. And we refer to this system as HAP-SER, and it's also an approximant of the ACP component of the cements, because all nanocrystalline apatite particles are coated by an amorphous surface layer of ACP. So here you see some redo results where the nitrogen-15 NMR signal dephasing is plotted for increasing dipolar decoupling times to the surrounding phosphorus-31. Here the data in black are from the polycrystalline phosphoserine powder. The data in red are from the HAP-SER, and then finally the data in green and blue are from the two cements. So from here we can see that the phasing behavior of the two cements are almost identical. And moreover, that the amino group in the cements are slightly, a little bit more distant from the inorganic phosphates as compared to the HAP-SER model system. We have also performed metadynamic simulations of the phosphoserine molecule in water that is in contact with the surface, a structurally disordered surface of apatite. And from these models, we calculated the nitrogen-15 phosphorus-31 dipolar second moment. You see the result here, along with that calculated from the crystal structure of phosphoserine. These results can be compared here with the redo NMR results. And as is typically seen for this type of experimentation, the experimental readout sequential moments are typically slightly lower than those you see by modeling or by theoretical or from a crystal structure. But here I would like to draw your attention to the excellent agreement we observe once we take the ratio between these two M2 values. And you see we have a very good agreement. So this suggests that our modeling is accurate. And over here you see the most stable surface bound molecular conformation of phosphoserine. Here the amino group is anchored at the surface via hydrogen bonds to inorganic phosphates. And here you see the most stable surface bound conformations of phosphoserine and serine. I can add here that all the details, they were not obtained by NMR, but from MD simulations. However, the simulations were validated through overall very good agreement with constraints from nitrogen phosphorus and carbon phosphorus readout. Then the black numbers you see here, they correspond to distances in picometer between the surface bound atom of the molecule with another atom species at the surface. So these are the directly bonded sites, so to say. And the molecular binding is basically involving two types of interactions. First, electrostatic interactions between the negatively charged oxygen atoms of the organic carboxy or phosphate groups that interact with calcium cations at the surface, as you can see here. Alternatively, there may be, as for the amino group, hydrogen bonding involved, as you see here, where the oxygen binds to a protonated phosphate group. And concerning the most stable phosphoserine binding, well, it binds by the amino and phosphate groups, and the phosphate group is by far mainly responsible for stabilizing the adsorption, meaning that it contributes the most to the bonding energy. And in the case of serine, it binds by the amino and the carboxy group, and here it's now the carboxy group that primarily stabilizes the binding. So I will get over to the last part of my talk, which concerns a new NMR crystallography method. We took the XRD structures of phosphoserine and its calcium salt, and we refined them by DFT calculations in CASTEP. That resulted in overall good agreements in both the carbon-13 and proton chemical shifts. Now our method is not relying in any way on chemical shifts, but it rather extracts either homonuclear or heteronuclear distances from dipolar recoupling to the NMR experiments. And you only need one experiment, but it needs to be recorded using a very short dipolar recoupling time to establish through space proximities. You see an example here of double to single quantum proton correlation spectrum from phosphoserine. In this spectrum here, all the signals from all 6 magnetically inequivalent proton sites are resolved. And what we then use is just the well-known feature that if you integrate the NMR signal intensity here, that one is proportional to the squared effective dipolar interaction of the proton pair. So what you do is that you integrate all these peaks, and then you take some structure model that you want to validate. It can be generated from any experiment or modeling, and then you calculate the sum squared dipolar couplings from the model structure, and then you compare it with the experimental data. Here you see some results. We got proton-proton distances from phosphoserine, where you see the NMR-derived effective distances plotted against those from the XRD structure before and after refinement by DFT. In the plots below here, you see phosphorus-proton heteronuclear distances, now also including the calcium salt of phosphoserine. And these were obtained by HETCORE. In both cases, as you can see, the DFT refinements improves the, gives a better structure, so to say. So let me finalize by thanking the people involved. Rennie Matthew, a former PhD student and postdoc in my group. He performed all the NMR experiments. Balsa Stevenson is our modeling guy. The cements were provided by Michael Piari-Polmer and Håkan Engqvist at Uppsala University, and the isotopically enriched phosphoserine was synthesized by Chris Spicer, Hélène Otefas, and Molly Stevens at Karolinska Institute. And then I would like to thank the Swedish Foundation for Strategic Research for funding, and I would like to thank you for your attention.
Questions for Matthias? Maybe I can lead off with one. So I saw several examples. Maybe it was the modeling where you used a pH of 4.5 to establish the environment. Is there a range of amorphous structures for different pHs that you evaluated, or, you know?
Yeah, I mean, the surface binding is pH dependent, let's say. So, but we include basically the pH value of the solution is kind of accounted for in the models, because you basically prepare a surface, and in this model you basically make the protonation of the phosphate groups to basically match that of the solution. So the surface is disordered, but it's not all the way to an ACP. And I can also mention that at the physiological pH for phosphoserine, then also the carboxy site also binds. So this is pH dependent. The reason we are using a low pH is the low pH of the cement pastes.
Okay, no, thank you. Please.
Did you ever try getting the BABA on the phosphorus 31 working? And if you did it confirm the results you got from the proton?
So, sorry, can you repeat the question?
BABA, right?
Did you try the BABA on the phosphorus 31? And if you did it confirm the results you got from the proton?
Let me see. You mean if I did a correlation experiment with using phosphorus?
Yes.
Yes, yes, we have. The problem with that is that you're not going to get any more information about the ACP in the cements, or perhaps you meant on the phosphoserine. Well, we have done that, but we have not analyzed the phosphorus distance. No. Sorry, I didn't get your question.
Any further questions for Matthias? Oh, one more. Tamara.
Maybe I missed this in the talk, but I was wondering how the correlation experiments that you did correlated with the mechanical properties, the difference in the mechanical properties that you stated in the beginning between serine and phosphoserine.
So again, sorry, I'm ignorant to the questions today.
Yeah, so maybe I missed that in the talk, but how do the correlation experiments and the distance measurements that you measured later, do they somehow correlate to the different mechanical properties that you showed?
No, I would I would say no. It's simply just rather a matter of how much you have of the amorphous phase. It's depending on the phosphoserine content. In this model, you can go all the way from here with low phosphoserine contents when the amorphous phase is low, all the way to where it basically dominates and you almost don't have any TCP. But I think that at the molecular level, you have the same interaction. So it's just a matter of how much you have of the phase itself concerning the properties.
Okay, thank you.
All right, seeing no other questions, let's give Matthias a hand. I do believe that closes out our session. Thank you all. See you tomorrow.
See you.